Hello, this is a review of Unit 3 for ENGR 201 final exam. And all of this is going over max and mins for multivariable calculus. So I'll just get right into it. So now we need to find and identify all local max and mins for this and or saddle points for this function where z equals f of x, y. So they prompt us to find fx, f double x, fy, f double y, and fxy. So fx is the partial of this function with respect to x, so it's going to be 6x minus 6y, and then f double x will just be 6, is again, fy is then going to become negative 6y squared minus 6x minus 12y. And then f double y would become negative 12y minus 12. And fxy it would just be negative 6. Yeah, negative 6. So now we need to find and identify all local max and min. So in order to do that, we set fx equal to 0 and fy equal to 0. So when we do that, we're then saying 6x minus 6y must equal 0, and we're saying negative 6y squared minus 6x minus 12y must equal 0. So looking at this first term, this first one right here, we're going to get, this is going to imply that x must equal y. So if x must equal y, we can then plug that back in to this x here. So then that would equal minus 6y squared. This becomes minus 6y, so it becomes minus 18y equals 0. So then we can factor this out. So we'll plot a 6 and a y. So we have 6y, y minus 3 equals 0. So then this implies y equals 0, y equals negative, or y equals positive 3. Because those are the only two terms that set equal to 0, which then implies that our points are going to be 0, 0, and 3, 3. Now we need to check to see if either of these points are saddle points. So then we have to apply the equation fx x times fyy minus fxy squared. And if it is positive, it's going to be a max or min. If it's negative, it's going to be a saddle point. So for 0, 0, this will be fxx is going to be 6, fyy will be negative 12, and I'm using these terms here, and I'm plugging 0 into them, and then minus fxy squared. So then this will equal negative 48 minus 36, which is obviously less than 0, therefore saddle point. And then we're going to have 3, 3, which again, so have 6 again, times, we plug in 3, I just realized I made a mistake. So I'm supposed to pull out, so let's go back real quick. I'm supposed to pull out a negative 6, which makes this y plus 3, which then makes this a negative y, which makes this negative y, negative 3. My bad. But it's a quick fix. And so we're going to have, so I plug in negative 3, so then we'll have 48 minus 12 minus 36 squared, which then will equal 6 times 36. Oh, not 36 squared. This is going to be negative 6 squared, which is 36. So 6 times 36 minus 36, which is then 5 times 36, which is greater than 0, therefore max or min. And then once you know it's a max or min, check f double x. And if that equals 6, which is greater than 0, it says it's greater than 0, therefore smiley face. So it's a local min because it's concave up. So therefore, and then we actually, I think now we need to actually calculate for our local max or min. So 0, 0 is a saddle point. We can leave that as this. We don't need to calculate it. But we need to calculate f of negative 3, 3. So f of negative 3, 3. It's going to be equal to 3 times negative 3 squared minus 2 times negative 3 cubed minus 6 times negative 3 times negative 3 minus 6 negative 3 squared. And then this will just equal, I'm just going to go to the answers because I don't want to do this algebra right now. Negative 27. So that equals negative 27. So it's going to be so that implies f of negative 3 comma 3 equals negative 27 is a local min. All right, move on to the next problem. So we're going to function with a certain region. So this is very similar to the previous problem, but the biggest difference is that now we don't have this infinite domain. Our domain is defined to what x and y can be in this region. So now we define interior points. So interior candidates, we just treat it like normal. Solve for fx. So fx equals 0, which then will equal 2x. Solve for fy. So that equals 0, and that'll be 4y minus 1, which implies that our point is going to become 0, comma 1/4. And then f of 0, 1/4 is 0 squared plus 2 over 16 minus 1/4. So it equals 1/8 minus 1/4, which equals negative 1/8. So that's how you test interior candidates. So boundary candidates, so along y equals 0. So along y equals 0 is this line right here. That was a terrible arrow. So that would include these 2 points. And y equal to 0. So now we just do f of x comma 0, which then just equals x squared, which then implies f prime of x to equal 0 is 2x, which then implies the point 0 comma 0, because so we found where f prime equals 0 for the function of just x, and then we had that which is 0, so we plug in y equals 0 as well, so it's 0, 0, and then f of 0, 0 equals 0. Now we check boundary candidates. So boundary candidates is going to include this point right here, which is negative 1 comma 0, and this point right here, which is 1 comma 0. So negative 1 comma 0 and 1 comma 0. So I already know they're both going to be the same, so I want to write this as f plus or minus 1 comma 0. This is going to equal plus or minus 1 squared plus 2 0 squared minus 0. So then this will just equal 1. Alright, now along y equals to x plus 1. So there's a new point we haven't touched upon yet, which is this point right here, which is 0 comma 1. So now let's try along y equals x. So it's going to be f of x comma x plus 1, which then equals x squared plus 2 x squared plus 2x plus 1. So I went ahead and expanded that, and then minus x plus 1, which then equals, it's going to become 3x squared plus 4x minus x, so 3x plus 2 minus 1 plus 1, take rid of that. F prime of x is going to equal 6x plus 3, which then implies equal to 0, which then implies x equals to negative 1/2, which then implies y equals positive 1/2. So f of negative 1/2 positive 1/2 equals 1/2 squared plus 2 times 1/2 squared. This would be negative. Then minus 1/2, so that will equal 1/4 plus 1/4 times 2, 1/2 minus 1/2, perfect, equals 1/4. And then our extra point f of 0, 1, which then just equals 0 squared plus 2 times 1 squared minus 1, which then equals 1. Now along x squared plus y squared equal to 1. So what I would suggest doing is looking to see how this would get your least amount of radicals out. So when we're looking at the equation, if we solved for y, we would definitely have a radical, but if we solve for x, x is squared. So we know that we have a radical, we're going to square it and get rid of it. And note that we're in the positive quadrant, so we're only dealing with the positive values of x and y. So when we have the absolute value, we can just take the positive version of it. So then solve for x. So x equals the square root of 1 minus y squared. Plug that into f of 1 minus square root of 1 minus y squared, comma y. And that will equal 1 minus y squared minus 2y squared, or sorry, plus 2y squared minus y. And that will equal y squared minus y plus 1. F prime of y equals 0, which then equals 2y minus 1, which then implies y equals 1/2. Which then implies x equals, and you can plug it in, but I know it's going to end up being 1/2. 1 minus 1/2 squared is going to equal square root of 1/4, which then equals 1/2. And then f of 1/2, positive 1/2. Earlier we calculated this right here. This is going to end up being the same thing, so that's equal to 1/4 as well, because I know that we're squaring the negative 1/2 x. Then f min, and in this case, looking at all the values, we have a negative, we have a 1/4, we have a 1, we have a 1/4, we have a 0, and we have a negative 1/8. Negative 1/8 is definitely the smallest out of all of these candidates. So negative 1/8, and at that point it is 0 1/4. Is that what that was? Back up. Yeah, 0 1/4. And looking at f max is going to end up being 1, but it's 1 at 3 different points, which is 0, 1 right here, and then at plus or minus 1, 0 right here. Alright, that's it for Unit 3. Good luck on Unit 3. This is pretty repetitive stuff. So